this section, we're learning a little more about the natural base e. Recall the compounding interest formula. When you have an amount that you start with, the principal, you can figure out how much you're going to have at the end of t years, given an annual interest rate. Remember, this is in decimals, for n number of compoundings per year. Let's take a look at this example here. You invest $1 in an account with an annual interest rate of 100% for 1 year. How much will you have when compounded yearly, daily, hourly, per minute, and per second? Okay, so here I've plugged in the correct values into the formula, right? You start with $1 and the annual interest rate is 100%, so 100% when you move the decimal over 2 times to the left side, right? It's going to be 1. It's for 1 year, so t is 1, and n is going to be what's changing. So if it's yearly, that's n equals 1, right? Because it's how many number of compoundings per year. If it's daily, n equals 365. If it's hourly, it's going to be 24 times 365. So if you do that in your calculator, you get 8760. And if it's per minute, you're calculating the number of minutes per year, so that's the hourly number times 60, right? And that's going to give you 525, 600. And then what about per second? So if things are being compounded per second in a year, you would multiply the per minute number by 60 again, giving you this value here. So this example is asking you how much will you have, right, in your account given these conditions when it's compounded at different numbers of times. Notice it's compounding more and more often throughout the year. Just one time to 365 all the way to, what is that, like 31.5 million times a year. Okay, go ahead. If you were to plug this into your calculator, you would get the following values. So notice here that even though your n value, the number of compoundings per year, is growing significantly larger, right? Your amount is not changing by that much. In fact, it's actually getting closer and closer to a specific number, like 2.71828. See how the numbers are getting closer and closer to a number? And that number is the number E. The number E is known as Euler's number, named after a mathematician named Leonard Euler. And it's an irrational number. It's a number that you cannot write as a ratio. Kind of like pi, right? You have non-repeating decimals, pi about 3.14159, ... Well, E is about E is 2.71828182845 ... And it doesn't actually repeat itself. It's a non-repeating decimal, irrational number. We just need to know that E is about 2.7. And one way that E can be defined is by this formula here, right? E is a number that this thing approaches, the total value of this function approaches as n gets closer and closer to infinity, right? Remember, as we plugged in n here, as n gets larger and larger and larger, our overall value gets closer and closer to the actual value of E. So recall the compounding interest formula. So you know you need to use this formula if you see the word compounding annually, semi-annually, quarterly, that type of a thing. But what happens if n gets bigger and bigger and bigger, that it's actually continuously compounding, right? It's continuously compounding, so n is approaching infinity. Then your formula turns into this one here. Okay, both of these formulas will be provided to you. You need to know when to use which one and how to plug them in. So if you see the word continuously compounding in the words, then you know to use this particular formula. Notice that E is the base here. Let's take a look at an example. It says you invest $100 for 10 years, compounded continuously. So that's the clue. This is a keyword that you are using this formula here, at an interest rate of 5%. How much will you have? So I'm looking to see how much I will have if I start with $100. Then E, right, you have the E button in your calculator, and E is a number about 2.7. Your rate 5%, we need to rewrite that in decimal form. And then the time, T, right, years, is going to be 10. So plug all of this into your calculator all in one go, and you should get, rounded to the nearest cent, $164.87. Just a quick reminder that when you see ln of x, it's actually the natural log of x. That is the same as log base e of x. Remember e, it's about 2.7, but we never write it this way. We always write it as ln of x, the natural log of x. It's just proper notation. Simplify the following, the natural log of e to the 3.2. So there are two ways that you can think about this. One way is that right here, natural log could be thought of as log base e, because that's what it is, right? Notice that log base e and e to the something exponentiated, right? These cancel each other or undo each other, giving you the final answer of 3.2. So that's one way to do this. The other way to do this is to move that power out to the front. Remember, you can multiply by 3.2 times ln of e. That's one of our properties. We're multiplying here. Well, what's ln of e? ln of e is log base e of e, right? E to the what gives you e, right? E to the first power. So this whole thing is just 1. So 3.2 times 1 also gives you 3.2 as your final answer. So two different ways to think about this problem. Okay, go ahead and try this problem here. Simplify e to the 2 ln of x. Okay, so right here, we can't quite cancel these guys out, right? Even though ln is base e, because that 2 is in the way. But we can move that 2 as a power, right? That's one of the properties, the power property. And now I can cancel out the base e with a log base e, giving us x squared as our final answer. Solve the following problem. The natural log of 8 plus the natural log of x equals 1, or ln of 8 plus ln of x equals 1. Recall that to solve logarithms, we want to have a single logarithm on one side. So if I condense this, since it's adding, I can multiply the arguments on the inside. So it's really ln of 8x equals 1. So remember, ln is really log base e. Okay, you may need to write this step. You may not need to. It's up to you. See that here, if I want to undo the log so I can get this guy by itself, we need to exponentiate both the left-hand side and the right-hand side by the same base. So we would exponentiate by base e. These cancel out and get 8x equals e to the 1, which is just e, and x equals e over 8. On a calculator section, if you round to 3 decimal places, you would get 0.340. Remember that when you're solving the equations involving logarithms, you always have to do a quick check to see that your argument is positive. So our answer is about 0.340, so if I plug it into any variables inside the argument, my overall value is positive, so I know that I can keep this answer. It is not extraneous. Go ahead and try solving this problem here. ln of 5 minus ln of x equals 2. What value of x would make this true, if any? So here I can condense the left-hand side by dividing, right? If I'm subtracting two logarithms, I can divide their argument inside a single logarithm. And now I can exponentiate both sides with base e, since ln is really log base e. So these would undo each other or cancel out, give 5 over x is equal to e squared. And here, be careful, x is in the denominator right now, so I can't just divide both sides by 5 or multiply by 5. We would need to first multiply by x, right? And then divide by e squared. So x is equal to 5 over e squared, which is about 0.677. Again, we need to check that our final answer makes all arguments positive. So if I look at the original equation here, the only argument with a variable is this one, and if I plug it in, the overall value of the argument is positive, right? It's just 0.677. So I know I'm good to go. This is my final answer.